right. So in this particular lecture, which is basically on LDV, the second lecture on LDV, so in the last lecture, remember that we talked about the demands on light source for LDV, and some of them were monochromatic, spatial and temporal coherence, linearly polarized, and well focused. And we also say that the laser beams exhibit a Gaussian intensity profile, which is exactly across the cross section of the beam. So normally, what we do is that if you try to focus Gaussian beam, so there is a low divergence angle. That means it is more or less collimated, which is what you see over here. So there is a little bit of divergence. Now, what you do is that you bring the beam and then you bring them to a focal length or a focal length L. And we will come across to this a little later as well. So these are basically your spherical wave fronts, and this is the region where wave fronts are more or less planar, so to say, in this waist where the focusing point is, and then it starts to diverge once again. So the idea is basically in this very small region in space where the beam is actually focused, the wave fronts are planar. And this will have a very significant role when we actually discuss LDV. So focusing is not a trivial thing, therefore. It has a small divergence angle. The wavefronts are spherical in nature. So when you actually, try to converge them or focus them, okay, it is only in this small region where they are more or less in a planar fashion. So this is a beam, a Gaussian beam, which is actually focused. Okay. So just keep that thing in mind when you actually do the stuff. So this is more on that. So this is a Gaussian intensity profile, as you can see over here. This is the focusing as we go on. Forget about the math part. The math part is not important at this particular point. So this is the beam waist, and there is this small region where you are supposed to get a more or less planar front, and then the decay of the field starts to happen, okay, relative to the z-axis. Z-axis is the propagation axis, okay, and the beam axis is with respect to the x-axis, for example. So this is how a typical Gaussian beam actually looks like. So it is in only a small region in space where you can actually expect some sort of a planar wavefront, and that is absolutely important for the LDV purposes, as we will see. And not only the LDV, even for PIV purposes. And when you try to form a laser sheet, for example, these things have to be kept in mind. Okay, that this is what we are actually dealing with. Now, the fundamental point of LDV is basically what we call the Doppler effect. Now, this is kind of very well known. Okay, and you have all studied it during your high school, perhaps. That what happens is that if you illustrate it in a very simple fashion, is that if there is a conveyor belt and then there is a receiver and there is a guy who is throwing cakes at you or placing cakes on the conveyor belt. Now so you receive the cakes at a certain frequency, right? He's putting the cakes at a certain frequency. You're receiving the cakes at a certain frequency. Now what happens is that if this guy now starts to move away or move in that particular direction, opposite direction, right? You will get cakes at bigger intervals or larger intervals. Now, if this guy starts to move towards you, okay, you will get the cakes at smaller intervals. Or in other words, you will have what we call a frequency change. If this is the nominal frequency that you would have got the cakes, a certain rate at which this guy is putting the cakes. If this guy maintains the same rate even, but he is moving away at a certain relative velocity with respect to this conveyor belt, what will happen is that if he is moving away, it is quite clear that you will get the cakes at a larger interval. You can see the interval is increased. If he moves towards you, you will get cakes at a much smaller interval. So there is a change in frequency depending on the velocity or the relative velocity of this transmitter. In this case, the transmitter is the guy who is throwing the cake and you are the receiver. So this is all very good. So this is something that you knew, that the relative velocity changes a lot of stuff. Now, if you have to put it in a mathematical fashion, so let's have the Doppler effect with a moving receiver. So you are the receiver, or in other words, you are this guy, the guy who is receiving the cake. Now, you may be moving at a certain relative velocity with respect to the wave propagation direction. So the wave propagation direction is given by ki being the unit vector in the ith direction. Okay? And you are moving at a certain velocity with respect to this kth vector, with respect to this direction of propagation. So the transmitter, so this guy is actually releasing a wave at a certain frequency, but you are moving away from that particular receiver at a certain relative velocity. Okay, so if you ideally would have been here, this would have been the frequency Ct by lambda. Okay, now that you are moving away, so this is the inner product between ui and ki. It's nothing but the component of ui in the kth direction or kith direction. So if you subtract the velocity, okay, you will get a new frequency comes into the picture. Okay, so now if we the new frequency is therefore the old frequency, okay, minus this particular factor, okay, which is ui ki by c. Okay, or in other words, the component of velocity in the kth direction divided by c. So the moving receiver receives a different frequency, which is f prime. So for him, the frequency has changed in the same way as this cake guy, it has changed. It has become something like an f prime. Okay, and in this case, as you can see, that the frequency is reduced. Okay, so that is what happens. Okay, so this is a moving receiver. Now, if we have a moving transmitter and a stationary receiver, say for example, you are standing at, you are maintaining your location to be fixed, and you have a transmitter which is moving at a certain velocity. Once again, this is a velocity ui, and it is giving out a wave in the Lith direction. This is again the unit vector, and you are that stationary receiver who is actually receiving it. All right. The initial, of course, the frequency is Ct by lambda, as you can see over here. Now it obviously has got reduced because C now is C minus ui Li, which is once again the inner product of the uth velocity in the Lith direction. So the frequency once again now in this particular case will be also reduced. So the stationary receiver receives a different frequency of the light. All right. So if you basically look at this, so if you have a receiver who is moving, you will see a different frequency. If you have a transmitter which is moving, you will also get a different frequency, which is the same way similar to this picture over here. Here, of course, the transmitter was the person who was moving. In this case, we have two situations in which the receiver is moving, and in the other case when the transmitter is moving. In both the cases, the stationary receiver perceives a different frequency. In this case, the moving receiver perceives a different frequency of the light. So these are the two things that happens in these two cases. So if you imagine, so in both cases, because of the relative velocity of either the receiver or the transmitter, you are receiving a different signal. So in one case, you yourself are moving, and that's why you see a different frequency. In the other case, you are stationary, but the transmitter is moving. As a result of that, you also get a different of the light that is coming to you. Okay, so this is the celebrated Doppler effect. Now, if you now look at it if you combine these two cases somehow, okay, how do you combine these two cases? In this case, you have an illuminating wave that is coming from some transmitter, and it's in the kith kind of a direction. You have a particle, okay, which is scattering this wave. Now, this particle is actually moving. at a velocity, some velocity ui. Okay, and then you have your receiver over here, which is now seeing a moving transmitter. So in this case, you can see there is a stationary, stationary transmitter and a moving receiver. For the screen, which is stationed here, which is going to collect this scattered wave, you have a moving transmitter and a stationary receiver. So, this part of the case basically corresponds to this. That means you have a stationary receiver, and this is your basically the scattered light that is coming out of the particle, which is moving at a velocity u. On the other hand, this part, the left-hand side of the segment, okay, is basically where there is a stationary transmitter but a moving receiver. So basically it's a superposition or the combination of these two cases which leads to what we are receiving on the screen. This screen is a stationary receiver, but because there is a particle in between, we are not directly looking at this wave, but we are looking at the scattered wave that is coming out of this particle, which is moving at a velocity ui in a particular direction, and you are monitoring it over here. Okay, so where you are monitoring, that depends, because we saw the scattering. The scattering, it scatters in all directions. So it depends on where your scattering screen is, your frequency will be according to that. Okay, so let us look at this particular thing. The frequency shift now is f double prime. Why it is f double prime? So there is a frequency shift that this particle sees, and then there is an additional frequency shift which the receiver here actually sees because of this moving particle. So therefore, this is f double prime is whatever frequency this guy or the receiver at the end or the photodetector actually looks at. So this is f double prime minus the original frequency, which is the frequency of the illuminating wave. This f double prime minus f is given by this relationship. Now you should also realize that ui li is a term which is basically the component of u in the direction of li, in the direction, whichever scattering direction you are actually measuring it. It is much, much smaller than c. Or in other words, your frequency shift is basically the original frequency, and this is the unit vector direction. So one is a kith direction, and the other one is the direction in which you are actually monitoring the scattering. So this depends. So if you are monitoring in the same direction, okay, which is like forward scattering, so this will be the same. This Li and Ki are in the same direction. If you are scattering it in the other direction, which is like backward scattering, okay, it will be the negative of that. So this is the premise. That means, so these are unit vectors in the forward scattering direction or the scattering direction in which you are measuring, and Li is basically the direction in which the light is in which the scattering is measured, and Ki is the direction of the illuminating wave that is falling on the particle, and the particle has got a velocity which is ui. Okay, so this can be any arbitrary direction in which the particle may be moving, and it's a combination of two cases. The left hand side is a stationary emitter and a moving receiver, and this right hand side is basically a case of a moving transmitter and a stationary receiver. So these two are the two cases that we already discussed in these two slides, the Doppler effect with moving receiver and Doppler effect with moving transmitter. Both of these two things were given. These are combined, and this is the final expression you get, with the caveat that ui is actually much, much smaller than c, which is the velocity of light. As a result of that, you get a frequency shift which is very, very small. You see this frequency is multiplied by ui by c. Ui is a small number, so therefore this becomes a very, very small, you are dividing it with a very large number. As a result of that, your frequency should go up quite a bit, because ui by c is a number which is much, much smaller than 1. So it is in the fraction, say 0.0000 something. Okay, as a result of that, this frequency therefore blows up. So if your parent frequency is whatever it is, say it is like 10 hertz, let's assume for the time being that if there is a frequency associated with it, say there is 10 hertz, okay, that is the frequency. So this gets scaled, and if this is like say 1 meter and this light's velocity is 10 to the power of 8, so it gets multiplied, it's like divided by 10 to the power of 8. So that is the kind of frequency shift that you are going to get. All right. So the Doppler shift, therefore, cannot be easily measured due to these two common factors that I mentioned. The frequency is in the range of 600 terahertz, which is beyond the response of any photodetectors that you will have. All right. So if we have a particle which has got a velocity of 10 meter per second, the frequency shift that is calculated from this expression, even assuming the maximum frequency shift that you can have, okay, it is approximately 3 into 10 to the power of minus 6%. So 3 parts in a million type of a percentage resolution must be resolved. So one is the base frequency is very high and the frequency shift is therefore very, very small. So this is onerous because you don't have photodetectors, you don't have that kind of a resolution. The other way of doing this is that you detect the Doppler shift which comes from the mixing of two shifted waves. So you mix two waves from two lasers and you observe the beat frequency, which is basically the principle of interferometry. So you observe the beat frequency and you use the beat frequency to measure what is the velocity going to be. Because you can see this expression is nice because you measure the velocity, you measure the, if we would have been able to measure this frequency shift, your velocity is automatic. You know the direction at which you are measuring the scattering. You can easily measure the velocity because this is the velocity that you are interested in. Remember, these are the tracer particles in the flow. So we are trying to measure the velocity of these tracer particles. Because once you measure the velocity of this tracer particles, you imagine, because they are small in size and all those things, they will represent the flow field. So in other words, this tracer particle velocity ui is the velocity of the fluid at that particular location and at that particular time, right? So ideally, if we would have been able to measure this delta f, then ui would have been pretty much a linear function. So you can actually then back calculate out ui in no time. But however, you have these problems because of the 600 terahertz and this very high this extremely, the frequency shift of approximately 3 part in a million resolution problem. So what you do, you mix two frequencies coming from two different shifted waves, and then you observe the beat frequency, and then you use the beat frequency to calculate the velocity, because your ultimate aim is to calculate the velocity. You are not interested in the optics, but you want the optics to be such that you are able to measure the velocity, right? So that is what it is. How do you do this? So you do this, you'll have Doppler shift with two illuminating beams. So say there is a beam illuminating wave 1, which is coming from one laser. This is the wave coming from another laser. It can be from the same laser also with a little bit of a, but they have the same phase essentially. So there is a half angle, which is phi, theta, whatever you call it. We have used different nomenclatures. This time it is phi. This is half the angle. So what you have over here is now two directions. One is Ki1 and Ki2. So these are coming at two different directions at you. And this is the particle concerned. And then there is the photodetector, which now measured the scattered wave that is emitted by this particular particle. So the particle is moving with a velocity ui. So everything else remains the same. This is the component of the velocity of the particle. This is u perpendicular, which is actually in the direction which is perpendicular to the z-axis. So if this is the axis, this is what it is. And Li is once again the direction at which your photodetector is placed to monitor the scattered wave. So what happens over here? If you consider one beam, you have a frequency shift of f1 double prime. If you have the second beam, you have a frequency shift of f2 double prime. So the Doppler shift of frequency is basically the difference in the shift of the two waves, okay, and which is nothing but, you can show this is actually 2 sine phi by lambda, lambda being the wavelength of the incident beams, multiplied by the velocity in the perpendicular direction, perpendicular to this particular axis. So you understand that F11 is basically nothing but the shift that you calculated here. Okay? This is one of the shift. So, okay, so this is the other shift that is coming from the second beam. So the difference between these two shifts, so there is a change in the Doppler shift. So Doppler shift itself means a shift in the frequency. What we are talking about here is the difference between the shift of two frequencies, right? Okay, and that is equal to the perpendicular component of the velocity, perpendicular to the z-axis, multiplied by 2 sine phi by lambda, where phi is basically the half angle and lambda is a wavelength of the incident beam. Here you can see that if this frequency comes out to be in the order of 1 to 100 megahertz, and there are photodetectors which can easily measure this shift in frequency. Now, if we can measure this shift in frequency and we know the half angle between the two incident beams, you can calculate the perpendicular component of the velocity, or the velocity component in the direction which is perpendicular to this axis, to this optical axis, right? Remember, it is not ui that you are measuring, it is u perpendicular component. So the Doppler shift is therefore proportional to the flow velocity normal to the optical axis. Remember again, the velocity of the particle is the flow velocity, okay, because that is what our assumption is. And it offers a linear response to velocity and therefore requires no calibration. So it is a linear response, as you can see. You know this, you know the half angle, you know the lambda, because these are the experimental setups. There is nothing dynamic about it. The FD is the only thing that you need to measure using your photodetector, and you measure then you can recalculate what is going to be the perpendicular component of the velocity. Nice and easy, and it comes out of the Doppler shift of the two beams, okay, and the difference between the two. So this is the optical configuration. So here, of course, we have used theta. So this is the incident wave, this is the incident wave, this is where they actually mate. So this is the measurement volume. As you can see that if you just do that y, the perpendicular component, you can see the n, okay, this is n, which is basically, there are two directionalities. So the n is basically E1 minus E2. That is given as 2 sine theta by 2 into Ex, which is the component in the x direction. And that is how you get this. You get this relationship because U perpendicular is nothing but what is Ux, okay, the beam in the perpendicular direction, and n is nothing but E1 minus E2, okay. This is just a vector subtraction, and that is what you get. This is the included angle. So this angle and this angle are the same, as you see. So this is how you get the 2 sine theta by 2. In this case, it is theta by 2. In the previous slide, this was half the angle. So it's basically the same, okay. So it is basically the half the angle into 2 sine of half the angle multiplied by 2 into Ex, where Ex is the unit vector in the x direction, and that is therefore it becomes the velocity in the x direction that we are actually measuring over here, okay. So what happens is that if the two coherent beams now intersect with each other, they create an interference fringe pattern. So these fringe patterns exhibit maxima and minima. So you have bright spots, bright lines and dark lines. So the fringe spacing depends on the wavelength and the intersection angle. So as you can see, this difference between two bright fringes is given by lambda divided by 2 sine phi, where phi is the included angle of the intersection, basically this. So these are the two coherent beams. They actually intersect with each other. They create an interference pattern, fringe pattern. This fringe patterns has got maximum and minimum intensity. This bright and dark. And this fringe spacing depends on the wavelength and the intersection angle. And this separation or the fringe spacing dependent on whatever laser beam that you are using. As you can see, smaller the wavelength of the beam, smaller will be the fringe spacing. Okay, and then it is also dependent on at what geometric angle that you have placed the two beams together. Okay, so these are the laser light that is scattered from small particles can be interpreted using the Moyer fringes. So these are the two laser lights. This is assumed that they are planar wavefronts, and this is the particle with a velocity v, or the effective velocity vp, that is actually traversing that fringe. You can see these are the fringes that are there. Okay, and this is the z-axis, and the detector is somewhere there. All right. So the interference fringe model is that the area in which these two beams intersect, an interference pattern can be imagined exhibiting constructive and destructive interference. The fringe spacing is given by delta x, which is lambda divided by 2 sine of half of the included angle. In this case, this is the whole angle, this is the half angle. Okay, a particle traversing the fringes will scatter alternatively high and low intensity lights, because as it passes through the bright fringes, it will scatter high intensity. When it goes through the dark fringes, it will scatter low intensity. The frequency of the light intensity changes can be used to determine the velocity once again. So this Fd is nothing but the velocity at which this, or the perpendicular velocity, divided by the delta x between the fringes, which is basically this. Okay, so the frequency of the light is frequency of the light intensity changes. It is what is actually used to determine the velocity of the particle in this particular case, and this is given by this simple relationship. This is the u, and this is the difference in the fringes. As you can see, if you make lambda small, these fringes will be smaller. So therefore, you can get more granularity on the velocity. Okay, and so this is how this is actually achieved. So in the next class, we'll move further on this.